In this video, we're going to talk about using the vector equation of a line to describe a particle moving in space. So previously, we discussed this definition, the vector equation for a line. So again, we're going to reiterate that. We have a line in space. There is some initial point P naught on that line with components x naught, y naught, z naught. And we can talk about this vector v, which is parallel to that line in space, and it's the same length from P naught to some terminal point P. So if we called that A is the same length as this vector V. And as we, reconsider defining those vectors, R naught is the vector from the origin to P naught. There's my R naught. And TV, right here, TV is the distance from P naught to P, right? So we said that P naught to P is some scalar multiple T of that vector V. So the resultant, R of T, that vector, is going to be from the origin to our point P. That is R. So I have R as a vector. I have R naught as a vector. And then this blue vector is V. So this original vector equation for a line in space, we can actually think about it as a particle starting at this initial position and moving in the direction of vector v to its terminal position p. So the initial position is represented by the r naught vector plus time times speed, the magnitude of v, times direction, the unit vector for v. And think about what time times speed gives us. TV, that's actually distance. So we have our initial position plus a distance in a specific direction. And this formula is working for a straight line motion. So let's consider this example in an application sense. For this example, we're going to look at a helicopter flying in a straight line motion. So the helicopter is to fly directly from the helipad located at the origin, which is convenient for us, in the direction of the point 1, 1, 1. So that's 1 unit in the x-axis, 1 unit in the y-axis, and 1 unit in the z-axis, at a speed of 60 feet per second. We want to determine the position of the helicopter after 10 seconds. So the first thing we're going to do is we're going to consider that equation as we just wrote it. We said that r of t, the r vector, our resultant vector, is the initial position plus t times the speed, which is the magnitude of our v vector, times that unit vector, u, right? Or r of t equals r naught plus t, the magnitude of the speed, times, that looks like a dot, I'll take that away, times v over the magnitude of v, which gives us the unit vector for that direction. So we need to know v. And it's helpful because we're starting at the origin and traveling to the point 1, 1, 1. So in this situation, we'll say my v vector is 1, 1, 1, or rather I plus j plus k. And we also need the unit vector for v. So the unit vector for v is just going to be v divided by the magnitude of v. So that's 1, 1, 1 divided by the magnitude of the vector 1, 1, 1. And the magnitude is the square root of the sum of the squares. So that in the denominator is going to give me root 3. I've got 1, 1, 1 over root 3, or all of those terms then become 1 over root 3. We can rewrite this as 1 over root 3 I plus 1 over root 3 j plus 1 over root 3 k. So this that we've just found represents my unit vector for v, right? Which is just v divided by its magnitude. And the speed, we know what the speed is because that's given. So we've got this speed value. And r naught, since we are starting at the origin, r naught is the 0 vector. That's my initial position. So r naught, this guy, is going to just be 0. So I'll rewrite that for us. We have r of t equals my 0 vector plus t times my speed, which is 60 feet per second, times this unit vector we just found, which is 1 over root 3 I plus 1 over root 3 j plus 1 over root 3 k. Now, since all of these terms have a 1 over root 3, I'm going to factor that out. That's 60 over root 3. And 60 over root 3, if I rationalize that, multiply by root 3 over root 3, that's going to simplify to 20 root 3. So what we have here is r of t. The 0 vector is gone. And then the 60 and that root 3 become 20 root 3 t. And what I have left for my vector there is just I plus j plus k. So this is the equation I would use. This gives me my resultant in terms of t, where we are, the location of this helicopter after traveling that speed. So we're asked to find the position of the helicopter after 10 seconds. So going back to this, the position after 10 seconds, and that's going to be r of 10. So that is 20 root 3 times 10 times I plus j plus k. So 20 root 3 times 10 is 200 root 3 times I plus j plus k. We can distribute that through, and this represents the vector 200 root 3, 200 root 3, 200 root 3. So this vector represents the position in feet from the initial position at the origin after the helicopter has been traveling at a speed of 60 feet per second for 10 seconds. So that means we are 200 root 3 out on the x-axis, 200 root 3 out on the y-axis, and 200 root 3 on the z-axis. And if we looked at the magnitude of this vector, if we squared and summed all of these and then took the square root, the magnitude of this vector is going to give us a distance of 600 feet. And that should make sense because the plane traveled 60 feet per second for 10 seconds. So 60 times 10 is 600 feet. That is the distance that it traveled. So traveling in this vector position, right, traveling in the direction of this vector for 10 seconds creates a vector that is the same direction, it just has a greater magnitude, right? And so Like I said, the magnitude of this r of 10 vector is 600 feet. And each of these x, y, and z components, those are all measured in feet. They're giving us that location, 200 root 3 feet out in the positive direction on all three axes, x, y, and z. So I hope that makes sense to you. And as always, email me if you have any questions.